Hello everyone, I'm José Antonio García, who in collaboration with Edgar Lopez and Dr. Wolfgang Bittenholz present these works entitled An Effective Model of QCD with Two Light Quark Flavors. When we consider a non-zero chemical potential, the Euclidean action of QCD and therefore the weight factor in the path integral become a complex number. When this happens, we no longer have the probabilistic interpretation of the weight factor, thus we can't generate configurations with this. To overcome this issue, a method known as reweighting is used. This means that we split the real part of the weight factor to generate configurations and let the imaginary part to be attached to the observable we want to measure. However, the contribution of the configurations to the observable mostly cancel each other out. To overcome the cancellation, we require huge statistics that grows exponentially with the volume of the system. This is known as the signed problem. The signed problem has prevented lattice QCD simulations at finite chemical potential. In this work, we study an effective theory of QCD with two massive but light quark flavors. This effective model doesn't suffer from the signed problem, so we can make numerical simulations at finite chemical potential. The Lagrangian of QCD with a first generation of massless quarks reveals a U2 cross U2 symmetry. In particular, there is embedded a SU2 cross SU2 symmetry known as the chiral symmetry. We know that this symmetry breaks spontaneously down to SU2. We can map this symmetry breaking to an effective Lagrangian, where the E fields are called classical spins, which live in the 3-sphere. This Lagrangian has the form of a O4 model, which in our case lives in a 4-dimensional space. When we add a degenerate quark mass, the chiral symmetry is explicitly broken down to SU2. This explicit breakdown can be introduced in our effective theory as an external magnetic field H, which accounts for the degenerate quark mass that breaks the O4 symmetry down to O3. Now we consider a small beta, which is the extent in the Euclidean time. In this approximation, the action is equal to the product of beta, which is the inverse temperature, and the Hamiltonian H. This simplification is known as dimensional reduction, that takes us from the 4-dimensional O4 model to the 3-dimensional O4 model. The 3D O4 model is endowed with topological charges. Skyrim in the 60s proved that the topological charge takes the role of the baryon number. Thus, our effective theory also accounts for baryons. In our model, the topological charge enters in the Hamiltonian multiplied by the chemical potential. Thus, we have the following Hamiltonian. The path integral is still a highly divergent term that needs to be regularized. We do this by means of the lattice regularization. So we have a discrete action lattice units where the lattice step size is A equals 1. Our last task is to estimate the magnitude of the external magnetic field. We found H in lattice units to be equal to 0.367. Physically, the H represented the pion mass. So, in summary, we have simulated the 3D O4 model with an external magnetic field as an effective model of two-flavor QCD with a degenerate quark mass. We're gonna monitor the temperature T where the crossover takes place to explore the QCD phase diagram with two massive quark flavors at a finite baryon density. This is done numerically using the so-called Wolf algorithm. Now, here we have the simulation parameters. We simulated the 3D O4 model with cubic volumes with periodic boundary condition. We have a magnitude of the external magnetic field in lattice units to be equal to 0.367. We use several chemical potentials in lattice units in the range from 0 to 2. We have simulated several temperatures and we have taken 50,000 measurements. In this figure, we observe the energy density of the system at different volumes and at some values of the chemical potential. We observe the energy density to be a smooth function of the betas. This is a first indication of a crossover instead of a first order phase transition, indicate the location to the critical endpoint. In this figure, we observe now the magnetization density versus beta. We also see a smooth behavior of the magnetization density. To plot the points in the phase diagram, we use two observables, the specific heat and the magnetic susceptibility. Here, we observe the specific heat at 2 in lattice units. We observe a peak which does not increase as dramatic as in a first order or second order phase transition. This indicates that we are indeed in the crossover region. We extract the beta of each peak at different volumes using a Gaussian ansatz. Also, the peak location doesn't move towards the divergence as the volume increases, which shows that it is in a second order phase transition. These betas will be used to extrapolate the crossover which occurs at infinite volume. This crossover beta will be used to plot the phase diagram in the end. We do the same with the magnetic susceptibility. We use a Gaussian ansatz to extract the crossover beta at each volume. Then we extrapolate to infinite volume to be plotted in the phase diagram. So however, the peak locations of the specific heat and the magnetic susceptibility don't coincide because it is a crossover and not a phase transition. Using these two observables, we plot the crossover region of the 3D04 model with an external magnetic field, which we use as an effective theory of two-flavor QCD. The red line corresponds to the crossover temperatures using the specific heat, and the green line using the magnetic susceptibility. In the range of chemical potentials we have worked with, we didn't observe the critical endpoint. But if we insist that this hypothetical point exists, we at least can give a lower bound equal to 250 megaelectron volts. In the literature, some other authors have estimated the location of the critical endpoint. Here, we observe the location of the critical chemical potential given by some people using several other methods, and we compare them to ours. Edgar Lopez, a collaborator of this project, focused in the chiral limit, that is massless quarks, and estimated a lower bound of 363 megaelectron volts. Meanwhile, while I estimated a lower bound of 250 megaelectron volts. We also compare the critical temperature estimated by these same authors and compare them to an upper bound given by Edgar Lopez, which is equal to 125 megaelectron volts. In conclusion, we use the 3D04 model as an effective theory to study the QCD phase diagram. We use an external magnetic field that accounts for a degenerate quark mass. We plotted the phase diagram to energies up to 250 megaelectron volts of the chemical potential mu b. However, a critical endpoint was not observed in this range of chemical potentials.